What if I told you that most of the universe is nothing, not darkness, not silence, but actual, genuine emptiness, a void so complete, so profound that it makes the word empty seem insufficient? Tonight, we journey into that emptiness. We drift through the spaces between stars, between galaxies, between the very building blocks of existence. We explore the vastness that separates everything from everything else. The infinite distances that make the cosmos what it is. Over the next 2 hours, we'll travel from our familiar Earth outward, measuring the growing emptiness as we move away from the warmth of our sun. We'll cross the boundaries of our solar system, venture into the gulf between stars, and peer into the cosmic voids that dominate the universe's volume. Along the way, we'll discover that empty space isn't quite as empty as we think. And yet somehow, it's far emptier than we can possibly imagine. The narration will be gentle. The pacing will be slow. There's no rush to understand every detail, no test waiting at the end. This is simply an invitation to contemplate the scale of existence, to let your mind wander through distances so vast they become almost meaningless, and eventually, to let those thoughts soften into sleep. So settle into a comfortable position. Let your breathing slow. Close your eyes if you wish. There is nowhere you need to be right now, nothing you need to solve or remember or worry about. The universe has been expanding for nearly 14 billion years, growing emptier with each passing moment. It will continue long after we're gone. Tonight, you're simply a consciousness floating through that emptiness, listening to the story of nothing, and discovering that nothing might be the most fascinating thing of all. Let's begin our journey into the infinite spaces between stars. Before we can comprehend the emptiness between stars, we need to understand distance itself. We need to feel it in our bones, to translate the incomprehensible numbers into something our minds can grasp, even if only for a moment. Stand outside on a clear night and look up at the stars. They seem so close, don't they? Pinpricks of light scattered across the darkness, near enough to touch if you could just reach a little higher. The moon hangs there like a lantern, Venus glows steady in the twilight, and the Milky Way stretches overhead like a river of light. But that closeness is an illusion. Those lights are separated from us by distances so vast that kilometers and miles become useless as units of measurement. We need something bigger. Let's start small, with a distance we can understand. The moon, our nearest celestial neighbor, sits approximately 240,000 miles from Earth. That's roughly the distance you'd travel if you drove around the Earth's equator 10 times. It sounds far, and it is, by human standards. The Apollo astronauts took 3 days to reach it. Light, traveling at 186,000 miles every second, takes just over a second to cross that gap. Now let's step farther out. The sun, the center of everything we call home, lies about 93 million miles away. This distance is so important to astronomers that they've given it a special name, the astronomical unit, or AU. 1 AU is the average distance between Earth and the Sun, our cosmic yardstick for measuring the solar system. Light from the Sun takes 8 minutes and 20 seconds to reach us. This means when you look at the Sun setting over the horizon, you're seeing it as it was 8 minutes ago. If the Sun suddenly vanished, we wouldn't know for over 8 minutes. We'd continue living our lives under what appeared to be sunlight, unaware that the source had already disappeared. Think about that for a moment. The thing that makes life on Earth possible, the blazing fusion reactor at the center of our solar system, is so far away that its light is always old by the time it touches your skin. You've never seen the sun as it is right now, only as it was in the past. Let's put this in perspective with a scale model. Imagine the sun shrunk down to the size of a large beach ball, about 2 feet across. On this scale, Earth would be a small marble about the size of a pea, sitting 200 feet away. That's roughly the length of a city block. Mercury would be even closer, Venus a bit farther in, and Mars would sit about 300 feet from our beach ball sun. The gas giants live farther out in our model. Jupiter, the largest planet in our system, would be a baseball nearly 1,000 feet from the sun, over 3 football fields away. Saturn, with its magnificent rings, would rest almost half a mile distant. Uranus would sit almost a full mile away, and Neptune, the outermost planet, would be positioned nearly a mile and a half from our starting point. But here's where it gets interesting. On this same scale, the nearest star, Proxima Centauri, would be another beach ball sitting over 10,000 miles away. That's the distance from New York to Tokyo, and halfway back again. The space between our beach ball sun and that distant beach ball star is almost entirely empty. A few grains of sand might represent asteroids, a few specks of dust could stand in for comets, but otherwise, nothing, just empty space stretching on and on and on. This is the first great truth about the cosmos. Objects in space are fantastically far apart from one another. The universe is not a crowded place full of colliding worlds and dense nebulae. It is, instead, a vast emptiness punctuated by occasional specks of matter, so widely separated that even traveling at the speed of light, the fastest possible speed in the universe, it takes years to get from one to the next. Light years. That's the unit we use for interstellar distances. A light year is the distance light travels in one Earth year, about 5.88 trillion miles, or 9.46 trillion kilometers. It's a distance so enormous that our brains can't really process it. We can say the numbers, write them down, do calculations with them, but feeling what that distance means, that's nearly impossible. Proxima Centauri, our nearest stellar neighbor, sits just over 4.2 light years away. That means the light we see from it tonight left that star over 4 years ago. When you look at Proxima Centauri, you're seeing it as it was 4 years in the past. If it exploded today, we wouldn't see the flash until sometime in the late 2020s. But even Proxima Centauri is relatively close on cosmic scales. The bright stars you see in the night sky, the ones that make up the familiar constellations, are tens, hundreds, even thousands of light years away. Betelgeuse, the red giant star in Orion's shoulder, sits roughly 500 to 600 light years distant. Estimates vary slightly based on different measurement methods. The light you see from Betelgeuse tonight left that star around the year 1400. During the early Renaissance on Earth, when Leonardo da Vinci was being born. The Milky Way galaxy, our home galaxy, is roughly 100,000 light years across. Light starting from one edge would take 100,000 years to reach the other side. Imagine that. The entire span of written human history, about 5,000 years, wouldn't even cover 5% of that journey. And the Milky Way is just one galaxy among trillions. Our nearest large galactic neighbor, Andromeda, sits 2.5 million light years away. The light we see from Andromeda tonight began its journey before humans existed, when our ancestors were still evolving in Africa. These numbers start to lose meaning, don't they? 4 light years, 400 light years, 4 million light years. After a while, they all just become very far. Our brains weren't built to comprehend such scales. We evolved to understand the distance from our cave to the water source, from the village to the hunting grounds. Distances measured in light years are so far beyond our intuitive understanding that they might as well be infinite. And yet, we can grasp them in a different way, not through numbers, but through thought experiments. Through imagination, through allowing ourselves to feel the scale emotionally rather than rationally. Close your eyes and imagine standing on Earth. You can see the moon in the sky above you, glowing white and familiar. Now imagine traveling to it. 3 days in a spacecraft, watching Earth shrink behind you until it's just a blue marble in the darkness. You arrive at the moon and stand on its dusty surface, looking back at the only home humanity has ever known. Now travel farther. 8 light minutes to the sun, but moving at spacecraft speeds, not light speed. It would take months to get there. Then onward to Jupiter, Saturn, the outer reaches of the solar system. Years pass. Earth is no longer visible to the naked eye. The sun is just another star in the sky, brighter than the rest, but no longer the overwhelming presence it once was. You reach Neptune, 30 times farther from the sun than Earth. You've been traveling for years, and you're still well within the sun's gravitational influence. The solar wind still reaches here. This is still, by any definition, part of our solar system. But ahead lies something different, a boundary, a place where the sun's influence fades, and the true interstellar space begins. The solar system we know, the 8 planets, the asteroid belt, maybe the copper belt, if you've read a bit about astronomy, is just the visible core of something much, much larger. If you made a list of everything in our solar system and measured the distances between them, you'd discover something remarkable. Most of what we think of as our neighborhood is empty space. The planets themselves, with all their mass and size, occupy an infinitesimally small fraction of the solar system's volume. Let's travel outward from the sun and measure that emptiness. Mercury, the innermost planet, orbits at an average distance of 0.39 AU from the sun. That's about 36 million miles. It's a small, cratered world, baked by the sun's heat, completing an orbit every 88 days. Between Mercury and the sun, nothing but solar wind and occasional comets. Empty space saturated with radiation, too hot for any spacecraft to linger. Venus comes next at 0.72 AU, then Earth at 1 AU by definition, Mars at 1.52 AU. These are the terrestrial planets. Rocky worlds relatively close to the sun. But even here, in the inner solar system, the distances are staggering. Earth and Mars are never closer than about 35 million miles apart. On our beach ball scale model, that's over 200 feet of empty space. Beyond Mars lies the asteroid belt, a region extending from roughly 2 to 3.5 AU from the sun. This is often depicted in science fiction as a dense field of tumbling rocks that spacecraft must carefully navigate. The reality is far different. The asteroid belt is so empty that spacecraft can pass through it with virtually no risk of collision. The asteroids, numbering in the millions, are spread across such an enormous volume that the average distance between them is over 1 million miles. You could fit all the asteroids together, and they'd form a body smaller than Earth's moon. All those millions of rocks, scattered across hundreds of millions of cubic miles, contain less mass than our planet's single satellite. The asteroid belt looks crowded on a map because we're forced to compress vast distances into a viewable image. In reality, if you stood on one asteroid, you likely wouldn't be able to see another with the naked eye. Jupiter, the first of the gas giants, orbits at 5.2 AU. Here, over 400 million miles from the sun, the character of the solar system changes. Jupiter is massive, more than twice the mass of all other planets combined. Its gravity shapes the orbits of countless smaller bodies. It has protected Earth throughout history by deflecting or capturing comets that might otherwise have struck our planet. And it's surrounded by a system of moons that form a miniature solar system of their own. The distance from Mars to Jupiter represents a significant gulf in our solar system. On our beach ball scale, Jupiter sits over 3,000 feet from Earth's marble, more than half a mile of empty space. If you were to travel from Earth to Jupiter in a straight line, moving at a steady 60 miles per hour. It would take you over 750 years to make the journey. Generations would live and die aboard your vehicle before arriving at the gas giant. Saturn, with its iconic rings, orbits at 9.5 AU. The rings themselves are a marvel. Hundreds of thousands of individual ringlets made of ice and rock, some just a few meters thick. But the rings are also mostly empty space. The particles that make them up are separated by distances far greater than their own size, held in formation by gravity and orbital mechanics. From a distance, they look solid. Up close, you'd see they're more like cosmic traffic, with each ice chunk hurtling along its own orbit, occasionally colliding but mostly just following the mathematical dance prescribed by Saturn's gravity. Uranus sits at 19.2 AU and Neptune at 30 AU. These ice giants mark the traditional outer edge of our planetary system. Neptune is 30 times farther from the Sun than Earth. Light from the Sun takes over 4 hours to reach it. If you lived on Neptune, the Sun would appear as nothing more than a very bright star, still the brightest object in the sky, but no longer a disk, no longer the overwhelming presence that defines Earth's daytime. The distance from the Sun to Neptune represents a rough boundary. Inside this sphere, the Sun's gravity dominates everything. Planets move in predictable orbits. The solar wind flows outward, carrying the Sun's magnetic field with it. This is the realm where the Sun's influence is direct and unmistakable. But beyond Neptune, things get stranger. First comes the Kuiper Belt, a region of icy bodies extending from about 30 AU to around 50 AU. Pluto, the famous X-planet, is part of this belt, just one of many icy dwarf planets and smaller bodies orbiting in the cold darkness beyond Neptune. The Kuiper Belt resembles the asteroid belt, but it's bigger, farther out, and made of ice instead of rock. Again, it's mostly empty. The objects in the Kuiper Belt are spread across an immense volume. Current estimates suggest the total mass is perhaps only about 1/10 of Earth's mass, distributed across billions of cubic miles of space. You could search for lifetimes and encounter only a handful of these distant, frozen worlds. Beyond the Kuiper Belt, somewhere around 100 to 120 AU from the Sun, lies the heliopause, the boundary where the solar wind can no longer push back against the interstellar medium. This is where our Sun's breath ends. Beyond this point, the charged particles that flow from the Sun mix with particles from interstellar space. The Sun's magnetic field, which has protected us throughout the solar system, finally gives way to the galactic magnetic field. Voyager 1, launched in 1977, crossed this boundary in 2012 after 35 years of travel. It had moved at over 38,000 miles per hour throughout its journey. It took 35 years to travel a distance of about 120 AU, or roughly 11 billion miles. Think about that, the fastest spacecraft humanity has ever sent into deep space. Moving at speeds we can barely achieve, even with our best technology. Took over 3 decades to reach the edge of the Sun's direct influence. And that's still not even close to leaving the solar system, because beyond the heliopause, far beyond where Voyager 1 now drifts, lies the Oort Cloud. Imagine a shell of icy objects surrounding the entire solar system, not a disk like the planets or the Kuiper Belt, but a complete sphere, surrounding us from all directions, extending outward into the darkness between our Sun and the nearest stars. This is the Oort Cloud, named after Dutch astronomer Jan Oort, who proposed its existence in 1950. It remains theoretical, never directly observed, never photographed, never confirmed by any spacecraft. We've never definitively identified an object as part of the Oort Cloud. We can't point our telescopes at it and say, there it is. All our knowledge about the Oort Cloud comes from mathematical models and inference. The evidence suggests it exists, inferred from the behavior of comets. Long-period comets. Those celestial wanderers that swing through the inner solar system once every few hundred or thousand years have to come from somewhere. Their orbits are extremely elongated ellipses, bringing them close to the sun before sending them back out into the distant darkness. By working backward from their trajectories, astronomers determined that these comets likely originate in a vast cloud of icy bodies far beyond Neptune, far beyond the Kuiper Belt, far beyond anything we can easily observe. Current theoretical models place the Oort Cloud beginning at around 2,000 to 5,000 AU from the Sun. That's thousands of times the distance from Earth to the Sun. On our beach ball scale model, where Neptune sat about 1.5 miles away, the inner edge of the Oort Cloud would begin somewhere between 25 and 60 miles from our starting point. And the outer edge, models suggest it could extend somewhere between 100,000 and 200,000 AU from the Sun, roughly 1.5 to 3 light years away. On our scale model, the outer Oort Cloud could extend out to nearly 400,000 miles, well beyond the distance from Earth to the Moon. Let that sink in. Our solar system, the Sun's sphere of gravitational influence, may extend halfway to the nearest star. We think of solar systems as compact, local things. But in truth, the Sun's gravity might reach so far into space that it takes light over a year to travel from the Sun to the outer edge of what's technically still our solar system. The Oort Cloud, if it exists as theorized, is a mysterious place. Models suggest it could contain billions or even trillions of icy bodies, comets waiting to be disturbed by a passing star's gravity and sent on long falls toward the inner solar system. These objects are thought to be remnants from the solar system's formation, bits of the primordial disk that never coalesced into planets, kicked out into the distant darkness by gravitational interactions with Jupiter and Saturn billions of years ago. They're called a cloud, but don't picture a dense cluster. The estimated density of the Oort Cloud, based on models of comet origins, would still be incredibly low. These icy bodies would be separated by millions of miles from one another. If you stood on one, the next nearest object might be too far away to see. You'd float in darkness, with the Sun appearing as nothing more than a bright star among other stars. Earth would be invisible. Even with a telescope, you would be alone in a way that's almost impossible to comprehend. Surrounded by the distant light of other stars, knowing that the entire solar system, everything humanity has ever known, everything that has ever lived, every person who has ever existed, all of it compressed into a single point of light, so far away it would seem infinitesimal. Voyager 1, our fastest deep space spacecraft, traveling at over 38,000 miles per hour, will take about 300 years to reach the theoretical inner edge of the Oort Cloud. 3 centuries. 14 generations of humans living and dying before the spacecraft even begins to enter this outer shell of our solar system. And once it enters, based on current models, another 30,000 years to traverse it. 30,000 years of traveling through the Oort Cloud before Voyager 1 would emerge on the far side, having finally, truly left the solar system. 30,000 years. When Voyager 1 launched, the year was 1977. If it takes 30,000 years to cross the Oort Cloud, it will emerge on the far side in roughly the year 2000 AD. Humanity as we know it will almost certainly not exist by then. Our civilization will have risen and fallen. Our species might have evolved into something else, or gone extinct, or spread across the galaxy. The Earth's continents will have shifted. Ice ages will have come and gone, and Voyager 1 will still be drifting through the Oort Cloud, its instruments long dead, its golden record carrying sounds and images from a world that no longer exists in the form it once did. This is the scale we're dealing with. This is the emptiness we're trying to comprehend, the space inside the theoretical Oort cloud, from the sun out to that 2 to 3 light-year boundary, is essentially empty. A few planets close to the sun, a scattering of asteroids and Kuiper belt objects farther out, and then, for the vast majority of the solar system's volume, models suggest there's nothing but occasional icy comets, separated by distances so vast that they effectively don't interact with each other at all. Each one would drift alone in the darkness, taking millions of years to complete a single orbit, never coming close to another object, never experiencing anything except the faint, distant glow of the sun and the fixed patterns of stars that barely change over millennia. It's a profound loneliness, an emptiness that's difficult to truly grasp. And this is just within our solar system, just the space that belongs to our star, the neighborhood we call home. The true gulf lies beyond, just over 4.2 light years. That's the distance to Proxima Centauri, the nearest star to our sun. In miles, that's about 25 trillion. In kilometers, about 40 trillion. In astronomical units, about 268,000. On our beach ball scale model, where the sun is a large ball 2 feet across and Neptune sits 1.5 miles away, Proxima Centauri would be another beach ball sitting over 10,000 miles distant. The width of the entire solar system, from one side to the other through the theoretical Oort cloud, would be about 400 miles on this scale. The distance to Proxima Centauri would be 10,000 miles, 25 times wider than our entire solar system. This is interstellar space, the gulf between stars, the vast, dark ocean that separates every sun from every other sun in the galaxy. And it's mostly empty, not completely empty. We'll get to that. But far emptier than anything we encounter within our solar system. Far emptier than the space between planets, or between asteroids, or between Kuiper belt objects. The interstellar medium is empty in a way that makes those other spaces seem crowded by comparison. Let's try to understand this emptiness by traveling it. Imagine boarding a spacecraft and setting out for Proxima Centauri. You leave Earth, past the Moon, zip by Mars and Jupiter, and the outer planets. You cross the heliopause and enter interstellar space proper. The sun shrinks behind you, becoming just another star. After a few years, you can't even tell which star it is without checking your instruments. After a decade, you've traveled about 200 AU, twice the distance from the sun to the heliopause. You're now farther from Earth than any human-made object has ever been. Voyager 1's current position is behind you. You are in territory no probe has ever reached, and you still have over 99% of the journey left to go. 100 years pass. You've been traveling at, let's say, 1% the speed of light, an incredible speed by today's standards, requiring technology we don't possess, but modest by science fiction standards. You've covered about 1 light year, roughly a quarter of the distance to Proxima Centauri. You look out the windows of your spacecraft. The sun is a bright star behind you, still brighter than other stars, but no longer obviously special. Proxima Centauri is a red star ahead of you, growing brighter but still not particularly impressive. And in every other direction, stars. Thousands of them, the familiar constellations of Earth's sky, barely changed even after 100 years of travel. Between those stars, nothing. Absolute darkness. No planets to pass, no asteroids, no comets. Just the occasional atom of hydrogen drifting past your ship. Empty space stretching in all directions, cold and dark and utterly silent. Another 100 years. You're halfway there. The journey has now taken 2 centuries. Everyone who was alive when you launched is long dead. Multiple generations have been born and died aboard your ship. Proxima Centauri is the brightest star in your sky now. The sun is still visible, still recognizable, but dimmer. You could easily miss it if you weren't looking for it. The view out your windows hasn't changed much. Still stars in all directions. Still darkness between them. You've been traveling for 200 years, and the scenery has barely shifted. The stars are eternal, patient. They don't care about your journey. They'll be here long after your ship is debris. 2 more centuries pass, 400 years since launch. Finally, after 4 centuries of travel, Proxima Centauri grows large enough to resolve as a disk rather than a point. You begin to detect its planets, the faint wobbles in its spectrum that indicate orbiting worlds. You've made it. You've crossed the interstellar gulf, traveled farther than light itself travels in 4 years, bridged the gap between stars. And what did you pass along the way? Almost nothing. A few atoms per cubic centimeter. Some very diffuse gas, perhaps a few drifting dust grains, but mostly empty space. Vast, profound emptiness. The journey took 400 years, and for nearly all of it, you moved through nothing at all. This is what lies between stars. This is the reality of interstellar space. It's not the colorful nebulae of science fiction shows, where ships move from one glowing cloud to another, where space is full of phenomena to encounter and navigate. It's darkness, silence, emptiness on a scale that makes human minds shut down from trying to comprehend it. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Estimates vary based on different counting methods. But the space between those stars is so vast that if you picked a random point in the galaxy, you'd have to be extraordinarily unlucky to find yourself near a star. Most of the galaxy's volume is interstellar space, dark, cold, empty regions where the nearest star is light, years away in any direction. Some astronomers have calculated that if you shrank all the stars in the Milky Way to the size of grapefruits and scattered them proportionally across a space the size of North America, they'd be separated by about 3,000 miles on average. The galaxy isn't a crowded place full of stellar systems jostling for space. It's an empty void punctuated by occasional lights, so far apart that their gravitational influence barely reaches each other. This changes how we think about the night sky. When you look up and see the Milky Way stretching overhead, you're seeing a band of light formed by billions of stars. But you're not seeing the galaxy as it truly is. You're seeing only the light, the tiny, bright points. You're not seeing the darkness between them. You can't see emptiness. But if you could, if human eyes could somehow perceive the true structure of space, you'd see that most of what you're looking at is nothing at all. The stars would still be there, but they'd be revealed as tiny islands in an ocean of void, so far apart that the distances would make you dizzy. And we're only talking about our galaxy. The spaces between galaxies are even larger, too. But interstellar space isn't a perfect vacuum. It's not truly empty. There's something there, sparse and thin, but present. This something is called the interstellar medium, the gas and dust that exists in the spaces between stars. And while it's far emptier than any vacuum we can create on Earth, it's not nothing. The interstellar medium has an average density of about 1 atom per cubic centimeter. 1 atom. In a space the size of a sugar cube, you'd find, on average, just 1 single atom. To put this in perspective, the air you're breathing right now contains about 30 quintillion molecules per cubic centimeter. That's 30 followed by 18 zeros. The air is, comparatively speaking, incredibly dense. The interstellar medium, with its 1 atom per cubic centimeter, is emptier than anything we can produce in our best laboratory vacuums. And yet, that 1 atom per cubic centimeter adds up over the vast distances between stars. A cylinder 1 meter square, extending from Earth to Proxima Centauri, would contain about 40 trillion atoms. That sounds like a lot until you realize it's only about a kilogram of hydrogen, roughly the mass of a liter of water. 4 light years of space contains less matter than a bottle of water. That hydrogen, that single atom per cubic centimeter, is mostly what the interstellar medium consists of. About 91% of the atoms in interstellar space are hydrogen, the universe's simplest and most common element. Another 8.9% is helium. The remaining 0.1% consists of heavier elements: carbon, nitrogen, oxygen, iron, and all the rest. These heavier elements, rare as they are incredibly important. They form the dust grains that float through space, the building blocks of future planets, the raw materials for life. The interstellar medium isn't uniform. In some regions, it's even emptier than average. In the hot, diffuse regions between clouds, the density can drop to just 0.1 atoms per cubic centimeter, or even less. These regions have been heated by stellar radiation and supernova shockwaves. Their sparse gas ionized into a plasma that shines these dense, molecular clouds would still be considered an excellent vacuum by laboratory standards. But in the context of interstellar space, they're immense concentrations of matter, thick enough to block visible light, full enough of material to collapse under their own gravity and form new stars. The Orion Nebula, one of the most famous star-forming regions in our sky, is a molecular cloud. It's about 24 light years across and contains enough material to form thousands of stars. But if you were inside it, you wouldn't notice the dust and gas that makes it appear as a glowing cloud in our telescopes is spread across such an enormous volume that you'd still perceive it as empty space. You'd see the hot young stars embedded in it, blazing bright and blue. You'd see a faint haze if you looked carefully, a subtle dimming of background stars. But you wouldn't feel like you were inside a cloud. You'd still feel like you were drifting through empty space. The dust in the interstellar medium is particularly interesting. These aren't the dust particles that collect under your furniture. Interstellar dust grains are microscopic particles, typically less than 1,000th of a millimeter across, made of silicates, carbon, and ices. They're so small that billions of them together would barely be visible to the naked eye. And yet, these tiny dust grains play an enormous role in the galaxy. They absorb and scatter starlight, making distant stars appear dimmer and redder than they actually are. They serve as the surfaces where molecules can form, providing the chemical foundations for complex chemistry in space. And eventually, they clump together to form asteroids, planets, and everything on them, including the atoms in your body. Every iron atom in your blood was formed in a dying star, expelled into space in a supernova explosion, and spent billions of years drifting through the interstellar medium, before eventually becoming part of the molecular cloud that formed our solar system. You are made of atoms that once floated alone in the vast emptiness between stars, separated from other atoms by distances that would take light hours or days to cross. That's worth pausing on. The atoms in your body once drifted through interstellar space. They were once part of that 1 atom per cubic centimeter, floating in darkness, rarely encountering another atom, moving on currents of cosmic wind for millions of years. They were part of the emptiness, and now they're part of you, temporarily collected together in a form that can think and feel and wonder about its own origins. In the densest parts of the interstellar medium, in molecular clouds where stars are forming, observations suggest that complex chemistry happens. Despite the incredible cold, temperatures just a few degrees above absolute zero, atoms appear to find each other, stick together, form molecules. They build elaborate structures, organic compounds dozens of atoms large. These molecules are fragile, easily destroyed by radiation from nearby stars, but in the protected hearts of dark molecular clouds, They seem to survive and even grow. Some of these molecules are familiar. Water is common in molecular clouds. So is carbon monoxide, ammonia, methanol. Others are more exotic. Long carbon chains, ring-shaped molecules. Complex organics that wouldn't survive a second in Earth's atmosphere, but persist for millions of years in the cold, protected darkness of space. When a molecular cloud collapses to form a new star and planetary system, these molecules are incorporated into the forming worlds. Some end up in asteroids and comets. Some are heated and transformed by the young star's radiation, and some, inevitably, end up on planets, where they become part of the chemistry that can lead to life. But we're not done exploring emptiness yet, because even the sparse interstellar medium seems crowded compared to the true voids of the universe. 2. Zoom out. Keep zooming out. Past Proxima Centauri, past the hundreds of stars nearest to the Sun, past the thousands of stars that make up our local stellar neighborhood. Keep going until individual stars blur together into a haze of light. What you're seeing now is not stars, but galaxies. Entire systems like the Milky Way, each containing hundreds of billions of stars, each so distant that its light has traveled for millions or even billions of years to reach your eyes. The universe, at this scale, reveals a structure that surprised astronomers when they first mapped it in the late 20th century. Galaxies aren't randomly scattered through space. They're organized into vast filaments and sheets, forming what's called the cosmic web. These filaments are like the strands of a three-dimensional spider web, with galaxies strung along them like dewdrops. Where filaments intersect, you find galaxy clusters. Thousands of galaxies bound together by gravity, the largest gravitationally bound structures in the universe. But what's between the filaments? What lies in the gaps of the cosmic web? Voids. Enormous, empty regions of space called cosmic voids. These are volumes that contain very few galaxies, stretching for hundreds of millions of light years across. They're the true deserts of the cosmos, regions where matter is so sparse that you might travel 100 million light years in any direction without encountering a single galaxy. Cosmic voids typically have diameters between 30 and 300 million light years. To put that in perspective, the entire Milky Way galaxy is only about 100,000 light years across. A typical cosmic void is thousands of times larger than our galaxy. The Oort void, one of the largest known supervoids, stretches roughly 330 million light years across. It's so enormous that if the Milky Way were located at its center, we would have discovered that galaxies existed much later in human history. Early telescopes wouldn't have been powerful enough to see beyond the void to the galaxy-rich regions beyond. The Oort void, despite its immense size, contains only about 60 known galaxies. A region of that size, if it had average density, should contain approximately 2,000 galaxies. So where did they all go? Why is the void so empty? The answer lies in the early universe. Shortly after the Big Bang, matter wasn't perfectly evenly distributed. There were slight variations in density, quantum fluctuations that were stretched to cosmic scales during the rapid inflation that occurred in the first fraction of a second. These density variations were small, but they mattered. Regions that were slightly denser than average had slightly stronger gravity. That extra gravity pulled in more matter, making them denser still, which increased their gravity further. Meanwhile, regions that were slightly less dense than average lost matter to their denser neighbors, becoming emptier over time. Over billions of years, this process amplified. The dense regions became the filaments and clusters we see today, vast collections of galaxies pulled together by gravity. The underdense regions became the voids, bubbles of space from which matter has fled, leaving behind only a thin residue of gas and the occasional small, dim galaxy that never quite made it to the party. Today, cosmic voids make up about 80% of the universe's volume. Let that settle in your mind. 80% of everything that exists is void space. The galaxies, with all their stars and planets, with all the light and life and complexity they contain, occupy only 20% of the universe. The remaining 80% is profoundly, almost unbelievably empty, but empty is relative. Even cosmic voids aren't perfect vacuums. They contain gas, very diffuse, very sparse, but present. The density in the deepest parts of a cosmic void is about 100 times less than the average density of the universe, which itself is only about 1 hydrogen atom per cubic meter. That means in the heart of a cosmic void, you'd find about 1 atom for every 100 cubic meters, roughly the volume of a large room. Imagine floating in the middle of a cosmic void. You're in a region of space hundreds of millions of light years across. The nearest galaxy is tens of millions of light years away in any direction, so far that even traveling at the speed of light, you'd need millions of years to reach it. If you had a telescope powerful enough, you could see those distant galaxies around the void's edge, forming a spherical shell of light surrounding you. But in every direction you look, the view is almost the same. Distant galaxies at the extreme edge of vision and nothing else. Just darkness. Just you, floating in the most profound emptiness nature has created. You wouldn't encounter an atom for hundreds of meters. Occasionally, over the course of hours or days, a single hydrogen atom might drift past you, a survivor from the Big Bang, moving on currents established billions of years ago. That would be your only companion. 1 atom every few hundred meters, 1 speck of matter in a volume that could contain entire planets. And yet, cosmic voids aren't completely dead spaces. Current theoretical models suggest that dark energy, the mysterious force thought to be causing the universe's expansion to accelerate, may dominate in voids. In regions where galaxies cluster together, gravity can overcome dark energy, holding structures together. But in the voids, where there's almost no matter to provide gravitational pull, dark energy appears to have free rein. These models indicate the voids could be expanding faster than the universe as a whole, growing emptier over time, pushing the galaxy, rich filaments farther apart. This suggests the voids might be playing an active role in the universe's evolution. They're not just empty spaces between things that matter. They could be participants in shaping the universe's future, potentially determining its ultimate fate. The universe is becoming more dominated by voids over time. The regions of space that contain galaxies are shrinking as a percentage of the total volume, while the empty regions grow ever larger. Billions of years from now, if current models of cosmic expansion hold true, cosmic voids will be even larger than they are today. The galaxies in our local group, the Milky Way, Andromeda, and their satellites, will likely have merged together into a single large elliptical galaxy. But beyond our local group, other galaxies will have receded so far that their light can no longer reach us. An observer on a planet around a star in that future galaxy would look out and see nothing. No distant galaxies, no cosmic web, just the stars of their own galaxy, and beyond them, perfect darkness extending in all directions forever. This is one possible fate suggested by our understanding of dark energy and cosmic expansion, though it remains theoretical and dependent on models that may change as we learn more. We are living in a special time, cosmically speaking. We can see a universe rich with structure, full of galaxies and clusters, with clear evidence of the Big Bang and cosmic evolution. Future observers, if these models hold true, will see something very different. They'll see a universe that appears empty, just one galaxy in an endless void. They'll have no way to know that there once were other galaxies, that the universe was once fuller, that the emptiness around them is a relatively recent development. Unless, of course, they have records. Unless they preserve the knowledge we're gathering now, the maps we're making of the cosmic web, the measurements we're taking of distant galaxies before they slip beyond the cosmic horizon. The universe's emptiness will swallow the evidence of its own past. Only memory will remain. Why doesn't the universe feel empty to us? When we look at the night sky, we see stars. When we look through telescopes, we see galaxies. The Hubble Space Telescope can point at a tiny patch of sky, no bigger than a grain of sand held at arm's length, and detect thousands of galaxies in that minuscule region. The universe appears to be full of light, full of matter, full of things. But that's an illusion created by light itself. Light travels immense distances. Photons from distant galaxies journey for billions of years across empty space to reach our telescopes. What we see when we look at the night sky is not the space itself, but the light that has passed through it. We see the sources, the stars and galaxies, but not the vast emptiness between them. Imagine standing in a desert at night. You can see the stars overhead, bright and clear in the dry air, but you can't see the air itself, can't perceive the miles of space between you and the stars. You see the lights, but not the darkness through which that light has traveled. The same is true of the universe. We see galaxies billions of light years away, bright and detailed in our telescopes, but we don't see, can't see, the billions of light years of empty space between us and them. This is why the universe seems crowded when you look at images from powerful telescopes. Every direction you look, you see galaxies. Point the James Webb Space Telescope at any patch of sky, and it will find thousands of galaxies, some so distant their light has traveled for over 13 billion years to reach us. The universe appears to be packed with galaxies, a cosmic ocean of light. But zoom in on any one of those galaxies. Examine the space around it. Look at the distances between it and its neighbors. Suddenly the emptiness becomes apparent. That galaxy might be 10 million light years from its nearest neighbor. The light you're seeing has traveled through 10 million light years of almost perfect vacuum, encountering perhaps a few atoms along the way before reaching your eyes. The cosmic web, those filaments of galaxies we discussed, looks impressive on a map. The filaments seem thick, substantial, full of galaxies. But remember the scale. A filament might be 100 million light years long and contain thousands of galaxies. But those thousands of galaxies are separated from each other by millions of light years of empty space. The filament looks solid from a distance, but up close, it's revealed to be a sparse scattering of matter through an overwhelmingly empty volume. Here's another way to think about it. Imagine you could see all the atoms in the universe. Every hydrogen atom, every helium atom, every heavier element. You could somehow perceive them all, glowing faintly in the darkness. What would the universe look like? Most of it would still be black, perfectly, utterly black. The atoms are so far apart, so sparsely distributed, that even with every single one of them glowing, most of the universe would remain dark. You'd see bright clumps where stars and galaxies form, regions where matter has concentrated into relatively dense collections. But between those clumps, darkness punctuated by the occasional lone atom drifting through space, separated from its nearest neighbor by distances measured in meters or kilometers. And remember, we're only talking about normal matter, the atoms and molecules that make up stars and planets and us. Normal matter accounts for only about 5% of the universe's total mass, energy content. The rest is dark matter and dark energy, substances we can't see, can't touch, don't fully understand. Dark matter, which makes up about 27% of the universe, is probably even more diffusely spread than normal matter. Dark energy, making up the remaining 68%, appears to be a property of space itself, uniformly distributed throughout the entire universe. So that true universe, if we could see dark matter and dark energy along with normal matter, might look even emptier than we imagine. The visible galaxies would be revealed as tiny specks of concentrated normal matter, embedded in vast halos of dark matter, all of it immersed in an ocean of dark energy that stretches uniformly in all directions, causing space itself to expand and emptying the universe further with each passing moment. The universe is not a crowded place. It's an incomprehensibly vast, profoundly empty place that happens to contain, here and there, small clumps of matter that have temporarily collected together. We are one such clump. The Earth, the solar system, the Milky Way, all of it is a rare exception to the rule of cosmic emptiness. And that emptiness is growing. The universe is expanding, carrying galaxies farther apart. The voids between clusters are getting larger. The average density of the universe is decreasing. Every second, space itself is being created, and that new space is empty. The universe contains the same amount of matter and energy it always has, but that matter and energy is being spread across an ever larger volume. Eventually, in the unimaginably distant future, one theoretical scenario suggests the universe could reach a state sometimes called heat death, a condition where all energy is evenly distributed, where all stars have burned out, where black holes have evaporated, where nothing changes anymore because there's no energy gradient left to drive change. At that point, if this scenario unfolds, the universe would be as close to truly empty as it's possible to be. Any remaining particles would be separated from each other by distances so vast that they would effectively never interact. Each particle would drift alone through an eternal, unchanging darkness, so far from anything else that it might as well be the only thing that exists. That's one possible ultimate fate of all this emptiness, to become even emptier still. Let's bring this back to human terms. Let's talk about what all this emptiness means for us, for our dreams of exploring space, for any hope we might have of traveling between stars. The fastest spacecraft humans have ever built is the Parker Solar Probe, which has achieved speeds of around 430,000 miles per hour during close approaches to the Sun. Though this is only possible when using the Sun's gravity for assistance, that's fast enough to travel from Los Angeles to New York in less than a minute. By any earthly standard, it's incomprehensibly fast. At that speed, traveling to Proxima Centauri would take about 6,500 years. That's longer than recorded human history. The Parker Solar Probe could have launched when the ancient Egyptians were building the first pyramids, and it still wouldn't have arrived yet. Voyager 1, launched in 1977, is currently moving at about 38,000 miles per hour relative to the Sun. Much slower than Parker Solar Probe's peak velocity, though still faster than any other spacecraft has traveled for an extended period. At this speed, Voyager 1 will take about 73,000 years to reach the distance of Proxima Centauri. It won't actually arrive at Proxima Centauri because it's not aimed in that direction. But the time frame gives us a sense of the challenge. 73,000 years. When Voyager 1 left Earth, the year was 1977. If it takes 73,000 years to reach Proxima Centauri's distance, it will get there around the year 75,000 AD. Homo sapiens as a species is only about 300,000 years old. 73,000 years ago, humans were still living in small tribes, barely beginning to spread out of Africa, using stone tools and struggling to survive. 73,000 years in the future, humanity might not exist at all. We might have evolved into something else, gone extinct, or transcended into forms we can't currently imagine. and that's to reach the nearest star. Most stars are much farther away. The average distance between stars in our region of the galaxy is about 5 light years. To reach an average star at Voyager 1's speed would take over 90,000 years. To cross the galaxy, to travel from one side to the other, would take billions of years, longer than the current age of the solar system. This is why interstellar travel is so difficult. It's not just an engineering challenge. It's a challenge that confronts the very nature of time and human life. We can imagine building faster spacecraft. We can envision nuclear propulsion systems, or ion drives, or even theoretical concepts like solar sails or antimatter rockets. But even if we increased our speed tenfold, even if we could travel at 1% the speed of light, an achievement that would require technologies we don't currently possess, it would still take over 400 years to reach Proxima Centauri. 4 centuries, 20 generations. The people who arrived would be the great, 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 great grandchildren of the people who launched. They would have been born on the ship. They would have lived their entire lives on the ship. Everyone they had ever known would have been born on the ship. Earth would be a distant memory, a mythical homeland they had never seen and would never see. This is the concept of the generation ship. A spacecraft designed to travel for centuries, maintaining a population that lives and dies aboard it, passing the mission down through multiple generations until finally, their distant descendants arrive at the destination. It's one way we can currently envision achieving interstellar travel with known or near future technology, and it raises profound questions. How would you maintain a society for 400 years aboard a spacecraft? How would you ensure that the 100th generation still cares about a mission started by their ancestors 20 lifetimes ago? How do you prevent social collapse, or mutiny, or cultural drift that changes the mission's goals? How do you deal with the psychological stress of knowing you'll never see the destination, that you're just one link in a chain, living your whole life in service of a goal you'll never witness being achieved? These aren't just practical problems. They're existential ones. They force us to confront what it means to undertake a journey across cosmic emptiness. Not just the physical challenge of crossing the distance, but the mental and social challenge of maintaining purpose and continuity across the time span required. Some theorists have proposed suspended animation. Put the crew to sleep for the journey, wake them when they arrive. But we don't know how to do this. The biological challenges of keeping a human body in stasis for centuries are immense. We'd have to stop aging without killing the person. We'd have to prevent cellular damage from accumulating. We'd have to hope that the systems maintaining the sleepers don't fail over the course of centuries. One malfunction, one power outage, and everyone aboard dies. Others propose uploading human consciousness into computers, sending just the information rather than biological bodies, but this remains deeply theoretical. We don't fully understand consciousness. We don't know if it's possible to transfer a mind from a brain into a machine, or if doing so would create something that's genuinely you, or just a copy that thinks it's you while the original dies. These questions blend philosophy with technology in ways we haven't yet resolved. The most realistic assessment, for now, is simple. We're limited by current capabilities. The emptiness between stars is, with our present technology and understanding, extraordinarily difficult to cross for human beings. We can send robotic probes. We can eventually send faster and more capable machines. But humans crossing interstellar space, that's centuries away at minimum and presents challenges that go beyond simple engineering. The emptiness defeats us, not with hostile forces or dangerous obstacles, but with simple, profound distance. There's nothing out there to stop us, it's just empty. But that emptiness is so vast, and we are so slow, that it presents barriers we haven't yet overcome. Some scientists speak optimistically about potential future breakthroughs. Perhaps we'll discover how to manipulate space-time more effectively, or find propulsion methods we haven't yet imagined. Though these remain speculative, perhaps we'll find ways to approach the speed of light more closely. The emptiness that seems so daunting now might become more manageable in the future, much as the Atlantic Ocean seemed impossible to cross until it wasn't. But these possibilities remain speculation. For now, for the foreseeable future, the spaces between stars remain beyond our easy reach. We can look, we can measure, we can study the light that crosses those empty light years. But we cannot yet go there ourselves. The emptiness is too great. Let's return to the question of what actually exists in all this emptiness. We've talked about the interstellar medium, about the 1 atom per cubic centimeter that floats through space between stars. But what does that really mean? What is it like, at the atomic level, to exist in that kind of emptiness? Picture a cube of space, 1 meter on each side. In your room right now, that cube would contain about 10 trillion atoms of nitrogen and oxygen, the molecules that make up the air you breathe. These molecules are constantly moving, colliding with each other millions of times per second, bouncing off surfaces, creating the pressure we feel as atmospheric pressure. Now picture the same cube in interstellar space. It would contain, on average, about 1 million atoms. Still sounds like a lot, right? 1 million atoms. But consider the scale. A cubic meter is large, about the size of a refrigerator. 1 million atoms in that volume means each atom is, on average, about a centimeter away from its nearest neighbor. A centimeter, the width of your fingertip. That's how far apart atoms are from each other in interstellar space. Each atom drifts alone in its tiny volume of space, rarely encountering another atom. When encounters do happen, they're gentle. Atoms passing near each other, perhaps exchanging energy or momentum, then continuing on their separate ways. These atoms are moving fast, though. The typical speed of an atom in interstellar space is about 10 kilometers per second. Faster than a bullet, faster than a rocket. They're not stationary specks, they're hurtling through space at incredible speeds. But because they're so far apart, collisions are rare. An atom might travel for years without hitting another atom. And these aren't just any atoms. They're the simplest atoms that exist. Hydrogen, with a single proton and a single electron. About 91% of the atoms in interstellar space are hydrogen. Most of the rest are helium, the second simplest element. The complex atoms that make up planets and life, carbon, nitrogen, oxygen, silicon, iron, are rare. They make up only about 1/10 of 1% of interstellar matter. This means the interstellar medium is chemically simple. It's almost entirely hydrogen and helium, the primordial elements created in the Big Bang. The heavier elements, created later in stars, are diluted into this primordial sea, rare spices in a bland soup. But here's something beautiful. Those rare, heavier atoms are essential. They're what make chemistry possible. Hydrogen and helium, by themselves, can't form complex molecules. They're too simple, too unreactive under normal conditions. But add carbon, oxygen, nitrogen, even in trace amounts, and suddenly you can build molecules, water molecules, carbon dioxide, organic compounds, the building blocks of life, in the densest parts of the interstellar medium. In molecular clouds where stars are forming, observations suggest that complex chemistry happens, despite the incredible cold. Temperatures just a few degrees above absolute zero, atoms appear to find each other, stick together, form molecules. They build elaborate structures, organic compounds dozens of atoms large. These molecules are fragile. easily destroyed by radiation from nearby stars, but in the protected hearts of dark molecular clouds, they seem to survive and even grow. Some of these molecules are familiar. Water is common in molecular clouds. So is carbon monoxide, ammonia, methanol. Others are more exotic, long carbon chains, ring-shaped molecules, complex organics that wouldn't survive a second in Earth's atmosphere, but persist for millions of years in the cold, protected darkness of space. When a molecular cloud collapses to form a new star and planetary system, these molecules are incorporated into the forming worlds. Some end up in asteroids and comets. Some are heated and transformed by the young star's radiation, and some, inevitably, end up on planets, where they become part of the chemistry that leads to life. The atoms in your body, every carbon in your DNA, every oxygen you breathe, every calcium in your bones, spent time in the interstellar medium. They drifted through space at 1 atom per cubic centimeter, separated from other atoms by centimeters or meters, moving through darkness and cold for millions or billions of years. They were part of the emptiness before they were part of you. This gives the emptiness a different character. It's not just absence, it's potential. Those sparse atoms, drifting through the void, are the raw materials for everything that will ever exist. Stars, planets, life, all of it starts with atoms floating alone in darkness, waiting to be collected by gravity into something greater. The universe is empty, yes, but that emptiness contains, scattered thinly through its volume, everything needed to create full places. The atoms are there, just spread out, dispersed, waiting. What does all this emptiness mean? Why does the universe need so much of it? What's the point of vast spaces where nothing happens, where no stars shine, where the nearest atom might be a meter away and won't encounter another atom for years? These aren't just scientific questions, they're philosophical ones. Questions about meaning, about significance, about what it means to exist in a universe that is, overwhelmingly, empty. Some people find the emptiness depressing. The universe is revealed not as a grand, full place teeming with life and activity, but as a void, endless darkness punctuated by tiny, temporary specks of matter that briefly flare into existence before fading back into darkness. In this view, everything we value, life, consciousness, art, love, is a fleeting exception to the universe's normal state of emptiness. We're anomalies, temporary disturbances in an ocean of nothing. But there's another way to look at it. The emptiness makes the full places special. If the universe were packed with matter, if stars were close enough together that their light overlapped and their gravity pulled on each other significantly, stellar systems would be chaotic. Planets would have unstable orbits. Close passes between stars would fling worlds out into space or send them plummeting into their suns. Life would struggle to develop in such a violent environment. The emptiness is what makes stability possible. It's what allows stars to have their own space, to develop planetary systems in peace, to burn steadily for billions of years without interference. It's what creates the quiet, stable environments where planets can form and life can evolve. The emptiness is not the universe's failure to fill itself. It's a feature, not a bug, a necessary precondition for complexity. Consider Earth. We orbit the Sun in a region of space that is, by cosmic standards, incredibly empty. The nearest star is over 4 light years away. Its gravity doesn't affect us. Its light doesn't outshine our Sun. It's just there, in the distance, no threat and no benefit. This isolation is what has allowed Earth to remain stable for billions of years. If we had a neighbor star passing through the solar system every few million years, life on Earth would likely have faced repeated extinction events from gravitational perturbations or increased radiation. The emptiness, in this way, has protected us. It gives us room, It creates the possibility for complex systems to develop and persist. There's also something profound about the relationship between emptiness and distance. The reason space is so empty is because it's so large. The reason it's so large is because the universe is expanding and has been since the Big Bang. The emptiness and the expansion are connected, two aspects of the same fundamental fact about our cosmos. This means the emptiness is, in a sense, time made visible. Each light year of empty space represents a year during which the universe has been expanding, during which space itself has been created and matter has been spread thinner. The vast distances we've explored in this journey are a measure of the universe's age, a record of cosmic history written in the spacing between objects. When you look at a galaxy a billion light years away, separated from us by a billion light years of empty space, you're seeing not just distance, but time. That space represents a billion years of expansion. The emptiness between us and that galaxy is, in a very real sense, a billion years old. It was created gradually, over the history of the universe, as space expanded and carried that galaxy away from us. The emptiness is the story of time itself. And finally, there's something humbling about the emptiness. It reminds us of our scale. We are small, our planet is small, our star is ordinary, our galaxy is one among trillions. And the spaces between all these objects, the emptiness that makes up most of reality, is so vast that human minds can barely grasp it. This could be depressing. It could make us feel insignificant, but it can also be liberating. The vastness of the universe, the profundity of its emptiness, doesn't diminish us. It just puts us in context. We are small, yes, but we exist. We are conscious. We can look out at all that emptiness and understand it, measure it, contemplate it. We can feel the appropriate awe. The atoms in your body came from space. They drifted through that emptiness for eons before coming together to form you. In a real sense, you are a piece of the universe that has temporarily organized itself into complexity. You are the universe, locally concentrated, looking out at itself and seeing mostly emptiness. But that emptiness made you possible. It gave the atoms time to travel, space to drift, quiet to persist. Without the emptiness, the fullness couldn't exist. So perhaps the emptiness isn't something to be afraid of or depressed by. Perhaps it's something to marvel at, a necessary background against which complexity can arise, the canvas on which the universe paints whatever brief pictures it creates. And we are one of those pictures, temporary, small, lasting only a cosmic eye blink, but here, conscious, aware of the emptiness around us and somehow, miraculously, alive despite it all. We've journeyed far tonight, from Earth out to the Moon, then to the planets of our solar system, past Neptune into the Kuiper belt, across the heliopause into true interstellar space, through the theoretical Oort cloud that may surround our sun like a vast, spherical halo, across the gulf to the nearest stars, out into the spaces between galaxies, into the cosmic voids where matter is so sparse that atoms are meters apart. We've measured the emptiness. We've tried to comprehend its scale. We've discovered that most of the universe is nothing, empty space, dark and silent, and profoundly alone. And now we return, back across those impossible distances, back through the voids and the interstellar medium, back past the theoretical Oort cloud and the Kuiper belt, back to the familiar planets, back to Earth, back to the small, warm place where life has somehow managed to exist despite the overwhelming emptiness that surrounds it. You are here, on this planet, in this solar system, at this moment in cosmic history. The atoms that make up your body have traveled through the emptiness we've been discussing. They've drifted alone through space. They've felt the cosmic wind. They've been separated from other atoms by distances that light takes years to cross. And somehow, they found their way here. They collected into this planet. They became part of the chemistry that led to life. They organized themselves into the complex pattern that is you. You are not separate from the emptiness. You are made of it. Your atoms are former residents of that one atom per cubic centimeter interstellar medium. They're former citizens of the void, but now they're here, temporarily gathered together, able to think and feel and wonder, able to look out at the stars and understand, at least in part, what lies between them. This is worth pausing on. The universe is mostly empty, but the parts that aren't empty, the stars, the planets, you, are extraordinary not because they're common, but because they're rare, because they're exceptions, because they represent a temporary victory against the prevailing emptiness. You are that exception, a brief organization of atoms that shouldn't be organized, a pattern in the noise, a flicker of complexity in an otherwise simple universe, and that makes you precious. Not in a grand cosmic sense. The universe doesn't care about you, doesn't notice you, will continue long after you're gone, but in a human sense, in the sense that matters to other humans, you are rare, you are temporary, you are a marvel of chemistry and physics that has somehow become conscious and aware. The emptiness doesn't diminish that. If anything, it emphasizes it. The vast spaces we've explored tonight make the full places more valuable. The darkness makes the light more precious. The silence makes the sound of your breathing, right now, more significant. So let's rest here for a moment, not thinking about the cosmic scale anymore, not trying to comprehend the incomprehensible, just being here, in this moment, in this body, alive and conscious in a universe that is mostly empty, but occasionally, miraculously full. Your breathing is slow, your body is relaxed. The thoughts that have carried you through this journey are beginning to dissolve, to soften, to fade into the background. The numbers and distances and concepts are blurring together, losing their sharp edges. This is good. This is right. You don't need to hold on to the details. You don't need to remember every fact, every measurement, every philosophical reflection. The journey was never about the information. It was about the feeling, the sense of scale, the quiet awe. And now that sense of scale can settle into your bones. It can become part of your intuition, part of how you understand the world. You know now, in a way you didn't before, just how empty space really is, just how far apart things are, just how rare and precious the full places are. That knowledge doesn't have to be conscious. It can drift in the background, informing your perspective without demanding attention, like the knowledge that the sun is far away. You know it, you feel it when you think about it, but most of the time it just sits quietly in your mind, not needing to be examined. The emptiness can be like that too, a quiet knowledge, a background truth that shapes how you see everything else. And as that knowledge settles, as it finds its place in your understanding, you can let the rest go, let the specific numbers fade, let the exact distances blur, let the philosophical questions dissolve. What remains is simple. The universe is vast, space is empty, and you are here, briefly, miraculously, defying that emptiness by existing. 2. Let your eyes close now, if they're not already closed. Let your body sink deeper into rest. The journey is complete. We've traveled farther than light travels in years. We've crossed distances that would take generations of humans to traverse. We've peered into voids that contain almost nothing. And now we return to this moment, this breath, this body. Outside, if you were to look, the stars are still there, still shining across the emptiness, still separated by distances so vast they seem to mock understanding. But you don't need to look. You don't need to think about them. They'll be there when you wake. The emptiness will be there. The universe will continue its slow expansion, creating more space, more distance, more nothing. Tonight, let it all go. Let the numbers fade. Let the distances blur. Let the philosophical questions dissolve into the darkness behind your closed eyes. You've traveled far. You've seen the emptiness. You've felt its scale. And now, you can rest. The universe doesn't need you to understand it right now. It doesn't need you to stay awake, contemplating its mysteries. It will continue whether you're conscious or not, whether you're thinking about it or not. So sleep. Let your mind drift. Let the thoughts slow and stop. Let the darkness of sleep merge with the cosmic darkness we've been exploring, until there's no difference between the two. You are safe. You are here. You are allowed to let go. The emptiness of space is patient. It has waited billions of years. It can wait until morning. For now, there is only this: your breath, your body, the gentle darkness of sleep approaching. Nothing to figure out. Nothing to remember. Nothing to do. Just drift. Let go. Sleep softly among the stardust, knowing that the vast emptiness we've explored tonight is, in its own way, what makes your existence possible. Rest now. The infinite journey between stars will still be there tomorrow. But tonight, you've traveled far enough. Let the emptiness hold you. Let the darkness comfort you. Let sleep come softly, naturally, easily. And when you wake, the stars will still be there, separated by all that nothing, shining their ancient light across the void. But that's for tomorrow. For now, there's only sleep, only rest, only the gentle dissolution of thought into the welcoming darkness. Good night, traveler. You've journeyed well. You've seen the emptiness and survived it. You've touched the infinite and returned. Now sleep. Among the starlust, among the silence, among the vast and beautiful nothing that holds everything. Sleep softly, sleep deeply, sleep well. Thank you for exploring the infinite emptiness with sleep among stardust. If you found peace in tonight's journey, please consider subscribing for more voyages through the cosmos. Until next time, rest well under the stars.